Hello, my name is Meredith Renaud, and this is my Physics 2212 Section X07 Lab 4 report on circuits and capacitors. The purpose of this lab was to predict the behavior of circuits containing resistors in series and parallel, to measure the conventional current and potential differences in the circuits using multimeters, and examine the behavior of ohmic resistors and capacitors. The physics principles I used in this lab were delta V equals Q over C, I equals negative dQ over dt, which were all useful in calculating R, the loop rule, and the node rule to calculate the conventional current. The results proved that the time for the capacitor to charge and discharge is equal, while the slope of ln of delta V over delta V naught is equal or approximately equal to -1 over the R value. In the beginning of the lab, we were asked to approximate the value of I1 and I2 of the very first circuit, which just happened to be in series. The EMF of that circuit would be 2 times the voltage of one battery, which is 1.5, so the total EMF would be 3. The R equivalent would be 47 ohms plus 100 ohms, which would equal 147 ohms. You can do this because the circuit is in series. That means that the I would be equal to the EMF divided by R equivalent, which is 3 divided by 147. So my approximation for I1, which would also be equal to I2, was 0.02 amps, and according to the ammeter, that was the value of the current running through the circuit. If you look in the bottom left picture, that is a similar circuit of what the AB values you see at the right side of the screen, except the wires were connected. This is the potential difference between the points. From A to B, it was -3 volts, BC 0, CD 0.959, DE 0, EF 2.041, FG 0, GH 0. And due to the loop rule, we know that the total of these added up is going to be equal to 0. The top right table includes the data that I used to make the graph on the left, excluding the voltage column. In order to find this data, I used the stopwatch and voltmeter using the description of part 3 of the lab. I paused the circuit for approximately each second during the 20-second time interval and recorded the voltage for that time. I then divided that recorded voltage by the initial voltage at time 0, which was 9 volts, which was the charge of the battery, and then took the ln of the value. That gave me the graph on the left. The slope of that graph is -0.01667. The calculated R that I got, based off of the physics principles from earlier, was 6. -1 over R is approximately -0.01667, or close enough. The bottom plot is the potential energy diagram through circuit 1. It's based off of the values from the last slide, from AB, B to C, and etc. From H to A would also be 0 volts, and the cycle runs continuously as long as the circuit is complete. The first additional question for this lab is, what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? If we use an actual ammeter, we would have a small resistance from the wires that it hooks up to. In the ideal simulated ammeter, this resistance was not there, so that our calculations looked prettier or more ideal. And what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. So the battery in the model would charge the capacitor almost immediately. However, the same thing would happen because of the wire, and there would still be a small resistance, thus making the charging of the capacitor and the decharging take a small amount of time more. Thank you for watching my Lab 4 report.